Okay, so this will be the last tutorial of this course, tutorial number 8. And again, this is mostly based on superconductivity. So let us try and solve the problems given in the assignment. Okay, so let me take the pen. Right. So question number 1 is tin has Tc of 3.7 Kelvin and Bc of 31 millitesla at T equal to 0 Kelvin. Then what is the minimum radius in millimeter? You have to calculate the radius in millimeter, correct up to first decimal place. Then you have to calculate that what is the minimum radius that is required for a tin wire if it is to carry a current of 200 ampere at T equal to 2 Kelvin. So basically tin is a superconductor, this is a superconducting material. AC is abbreviation of superconductor. So it has a Tc that is mentioned to be 3.7 Kelvin, and it has also a critical field or critical magnetic flux density value which is mentioned to be 31 millitesla. Okay, and this Bc value is at particular T equal to 0 Kelvin. So from earlier tutorials and lectures also you know that this critical magnetic field in a superconductor has a temperature dependence, and you know that formula. I'll be writing that down in a while. So basically, because it has a temperature dependence, so you have to mention that what critical field value you are talking about and what temperature. So that is why they have mentioned in the question that this Bc value is actually at T equal to 0 Kelvin, or this is at Bc, this is the Bc at equal to 0, or in short Bc bracket 0. That means the critical field value at 0 Kelvin temperature. And Tc is the normal, the transition critical temperature above which tin becomes normal to superconducting to normal material is 3.7 Kelvin. And then this asks that what is the minimum radius required for the tin wire if it is to carry a current of 200 ampere at T equal to 2 Kelvin. So then you have it is mentioned that if your temperature is now not 0 Kelvin but it is at finite 2 Kelvin temperature, and the wire has to carry a current of 200 ampere, then what should be the minimum radius that is required for the wire? Okay, right. So that is what we need to calculate. So let us go to the blank part and try to solve this problem. So this is question number 1. This asks that T is the material which is a superconducting material. It has a Tc or critical temperature at as 3.2 Kelvin, right? So all these two temperatures that is mentioned in the question, one is 0 Kelvin or even at T equal to 2 Kelvin. Both are, you can see that both are T below Tc. That means both the temperature scales are such that it is below the transition temperature of tin. That is, if the external magnetic field has B less than Bc, then at 2 Kelvin tin will be superconducting and thus carry current with 0 resistance. Why? Because since it is mentioned that Tc of tin is 3.2 Kelvin, and in the question it is asked about 2 Kelvin, so 2 Kelvin is already below Tc. That means if there is no external magnetic field disturbing the Cooper pairs, then that this 2 Kelvin temperature will be sufficient for the tin material to remain superconducting. But if the external magnetic field causes a flux density B that is greater than the critical flux density of the superconductor, then obviously even if you are below Tc, it will still change the superconductor material into a normal material. So this is a commonly known concept that we already have studied in the past 2 lecture series and in the tutorial session even. So basically here you have to first remember what is the temperature dependence of the critical field in a superconductor. So let us write that down, that BC bracket T, that means it is the critical field value at some finite temperature point T, that is equal to BC bracket 0, which means this is the critical field temp value at or critical flux density value at the T equal to 0 Kelvin temperature into 1 minus T by Tc whole squared. Okay, so this is the formula. If you remember, we have also used it multiple times before in the earlier tutorials as well. So this is your temperature dependence of the critical field, right? So here in the question it is mentioned, if you remember, that BC0 equal to the critical field value at T equal to 0 Kelvin, and for T what was the value is that 31 millitesla, and sorry, Tc was not 3.2 but 3.7 Kelvin. So 30, this is T equal to Tc equal to 3.7 Kelvin, and your BC 0 value is equal to 31 millitesla, or 31 into 10 to the power of minus 3 Tesla. And your T, at what temperature you need to calculate the final result is T equal to 2 Kelvin. So first we will calculate that what is the critical field value at T equal to 2 Kelvin. So BC at T equal to 2 Kelvin equals BC0 is the direct value, you substitute that here. So this is 10 to replace that here. So this is 31 into 10 to the power minus 3 into 1 minus T is 2 divided by Tc is 3.7. This whole thing whole squared bracket. Okay, so we have to calculate this. Now let us use our calculator and directly just calculate this part. So if I just calculate it, so this is 2 by 3.7 whole squared, 1 minus that, and into 31 into 10 to the power of minus 3. Right. So this is, I am getting 0.0219 Tesla, which is nearly equal to 0.022 Tesla, or nearly equal to 22 millitesla, right? Sorry, yeah, so this is 22 millitesla. So this is the critical field value at 2 Kelvin temperature, right? So now it was asked that what is the minimum radius of the wire that is required. So if the radius of the wire equal to R, say, and current that is flowing through the wire is I, okay, and it is asked in the question that if your current that is required to flow in the wire is 200 ampere, then what is the minimum value for that? What is the minimum value of the radius of the wire that is required for that? Okay, so basically this is simple, that you know that if there is a current flow, it will cause a magnetic field, right? So if there is a current flow through the wire, then it will cause a magnetic field of its own. So basically we have to relate this current with the magnetic field value that we have calculated for T equal to 2 Kelvin in the superconducting state of the T. Okay, so basically you know that if you are talking about flux density, then flux density B becomes mu naught times H, where H is the external field, mu naught is the free space permeability, and B is the magnetic flux density, right? So in this case, your earlier information was about the flux density, not the magnetic field. So sometimes people generally call like convention, it is not actually term-wise right to call B as external magnetic field, because B is not the field, but generally B is just notation for the magnetic flux density that is caused by the field, okay, and the field is actually given by this notation of H. But however, sometimes many of the people, they actually mix up the terminologies, and sometimes I also may call B as the external magnetic field, but do not get confused by that. You have to remember that it is just a like notational term. So you have to remember that if I am calling it B, then it is obviously magnetic flux density, which is coming from the external magnetic field H, and the only difference between B and H is sitting here, which is this mu, or which, because there is no other material present, so it will be for a free space permeability, and that is why it is mu naught. Otherwise there will be other values, but because it is free space permeability, so it is mu naught. And if there is another magnetic material present, and it is not vacuum, so then it will, instead of mu naught, it will be mu, because then your mu will be mu naught into 1 plus chi, where chi is the susceptibility for the material that will be additional in this case, right? So this is well known. And another thing, you know that your B equal to mu naught into I by 2 pi r. Okay, so this is the magnetic field that is produced by a current flow I through a cylinder of radius r. Okay, so let's say this is the cylinder, this is the axis of the cylinder. Sorry, let me draw it once again. Okay, so let's say that this is your cylinder, and this is the current that is flowing through the cylinder. This is the axis, let's say, and you have a wire, which is basically, you can take it as an equivalent cylindrical form, right? So you can take wire which is cylindrical in nature, like this, and the radius of the wire, let's say, is r. Okay, so then in that case, if this I current is flowing, so obviously this is in upwards direction. So if you use the right hand rule, then you will see that your current for your field that will be produced by this current will be in the, like, in the anti-clockwise manner, right? So it will be like, this is this, then the field, sorry, the field lines will be like this around the where graph loop. So if this is in upwards direction current, so then the field will be in the anti-clockwise direction, right? So this is the field B, and in this case your B will be following this formula, that it is mu naught I by 2 pi r. But because B equal to mu naught H, so you can write that your H equal to basically I by 2 pi r, right? So this is the case. Now in this case, it is asked in the question that your I equal to 200 ampere and your mu naught value is known. This is a standard value, 4 pi into 10 to the power of minus 7. I think it is an SI unit, I think ampere meter, but you have to check that. But let's say it is an SI unit, and then R is the radius of the wire, that is unknown, we have to calculate that, and B is nothing but your critical field value at equal to 2 Kelvin, right? So let's say, because that is the only information that we have about the field at equal to 2 Kelvin, so that is why we choose the field here to be the critical field at equal to 2 Kelvin, which is given as 22 millitesla, that we have calculated just a moment ago, right? So now if all the things are known, then the only remaining unknown thing is R. So R becomes, R take it upside and other things come downside. So this is mu naught I by 2 pi. So R equal to mu naught I by 2 pi B. So that is equal to 4 pi into 10 to the power of minus 7 into 200 divided by 2 pi into 22 into 10 to the power of minus 3, right? So this is basically 2 pi and 4 pi makes it 2. So 2 and 22 becomes 11. This is 2 into 10 to the power of minus 7 into 10 square. So 2 into 10 to the power of minus 5 it becomes. Then it is divided by 11 into 10 to the power of minus 3. So this is 2 by 11 into 10 to the power of minus 2. Because this comes up, so this makes it minus 2. Now this is equal to 2 by 11 is 0.18. So it is 0.18 to the power of minus 2. Or it is 1.8 into 10 to the power of minus 3. And because this is all is in SI unit, so R will be, this answer will be in meter. And because it has a 10 to the power of minus 3, we can write it as 1.8 millimeter. Okay, so that is your answer, right? So basically, not why I am saying that this is the minimum value of the radius that is required for this current flow. The trick is in the concept that we have chosen the field to be the critical field, or B is chosen to be the BC at equal to 2 Kelvin, right? That means if R equal to R minimum, this is the minimum value that is required for this current flow is 1.8 millimeter, and so then your B becomes mu naught I by 2 pi R minimum, where I equal to specifically 200 ampere. Then this field gives you the critical field at T equal to 2 Kelvin. So the current 200 ampere in a minimum radius of the wire of 1.8 mm will produce a magnetic flux density that is same as the critical flux density of the material at that same temperature of 2 Kelvin. That means after this field, okay, after this field, the tin material will not remain superconducting anymore, but it will become a normal conductor, and it will have a dissipation when it flows. There is a current flow through the superconductor. Also, there is another thing is that in superconductors, because it can actually repel the magnetic field, or any kind of magnetic flux lines cannot penetrate the superconductor in the superconducting phase or below TC. That is why this is the maximum you can go in terms of the radius, because by this radius you are hitting the maximum limit of the field you can go up to, that is the critical field value. So you can go maximum up to this BC equal to 2 Kelvin, because beyond this tin will become normal and will not carry current without resistance anymore. So that is why this is your maximum limit that you have to hit, that for R equal to R minimum, which is 1.8 millimeter, you hit your maximum value of field that you can go up to remaining keeping the material as a superconducting material and not letting it become normal. So that is his BC value, and this is a R minimum, because if you choose R greater than R minimum, then because your magnetic flux density is inversely proportional to R, so if your R is greater, then your B becomes smaller. Then the field produced will be even smaller than BC at equal to 2 Kelvin. Okay, so that means you are in a safe limit, that whatever this current 200 milliampere, 200 ampere is when it is flowing through the wire, it is producing a field. That field will not exceed the critical field value for the material at equal to 2 Kelvin if you keep the radius of the wire on the lower end, right? So basically, I made a wrong statement, that if you choose your R to be greater than this R minimum value, then your obviously B is inversely proportional to R, so even the field that is produced by the current 200 ampere becomes very small or smaller. And you know that if the field is smaller, then it is obviously will be less than the critical field value of the material, and that is why it will be able to carry current without resistance or with zero resistance. But if the radius of the wire is even less than that, then B, because it is inversely proportional to R, B becomes large or B increases, and if B exceeds BC at equal to 2 Kelvin, then there will be resistance in 200 ampere, which is a huge current flow. So keep tin as superconducting, to keep the B produced by the current less than BC equal to 2 Kelvin, the minimum radius equal to 1.8 mm, or in other words R can be either 1.8 mm or even greater than that. That will not bother us because that only ensures that your B is less than equal to BC, which is the most important for the dissipationless current flow in the wire. So that is how you get the answer, that the answer is 1.8 mm. Okay. So obviously we get the exact result, that is in the given answer range, that is between 1.7 and 1.9. So we get 1.8 mm. Okay. So first question is done. Then second question says that second question says that consider the expression for binding energy of two pair pairs, which is this expression equal to 2 h cut omega t divided by 1 minus exponential of 2 by lambda, where lambda is some constant. Then for lambda much smaller than 1, what will be the proper option? Okay. So if this is the binding energy of the Cooper pair, then you know that the condition is that lambda is some constant, and for lambda much smaller than 1, what will happen? So if lambda is much smaller than 1, then 1 by lambda will be much greater than 1, right? Or 2 by lambda will be much greater than 2, or exponential of 2 by lambda will be also very large, because if you have an exponential and you give it a term in the inside the exponential that is actually very large, then it will be obviously a very huge quantity, and that will be the mostly dominating factor in the whole term. Okay. So that makes this because e to the power of 2 by lambda is very large, because your lambda is much smaller than 1, then your 1 minus exponential of 2 by lambda, where this exponential of 2 by lambda is very much and much stronger, and right, so this you can like approximate it to be e to the minus exponential of 2 by lambda, because you can ignore, then this one you can ignore by the presence of this exponential of 2 by lambda. Okay. So because in this case 1 minus exponential of I think I should not box it like this, because otherwise creating confusion. So this is just 1 minus exponential of 2 by lambda, because your exponential 2 by lambda value is very large, that we can neglect with respect to this 1 value at the front. So that we can this term is very large, so we can neglect 1 or ignore 1 with respect to this value only. So that makes this is equal to 2 h cut omega t divided by 1 minus exponential of 2 by lambda. 1 minus exponential of 2 by lambda, which is nearly equal to 2 h cut omega t divided by minus, because you have ignored the 1, minus exponential of 2 by lambda, which is nearly equal to minus 2 h cut omega t exponential of 2 by lambda. Or this becomes, so let us choose the right option, that 2 h cut omega t to the power of 2 by lambda with a minus sign. So I think this is oh sorry, so this is not the right option, because this has no minus sign, but in this case there will be a minus sign. Sorry, I have also missed it here, that so this is just minus 2 squared omega d to the power of minus 2 by lambda. So the right option will be this option. Okay. Now, 1 second, just let me check if it is recording or not. Right, so it is fine. Then question number 3 says that consider the following statements A to D regarding qubits and quantum computer and choose the correct option. Okay. So first option is that qubits can store more energy than bits, which is obviously true because classical bits does not have as much information storage capacity as qubits can have. It can also pass like carry much more information than the classical bits. And so I'll discuss about qubits a bit in detail later in the blank page. Right now let us choose the correct options. Second is that qubit can store as much memory as we want. That is not true. Qubits can also store the energy depending on the state of the qubit, right? So it will not have any like as much memory as we want. That is not a correct statement. So this is wrong. If there are n qubits in a quantum computer, then it will have n square different states. That is again wrong because if there are n qubits and each of the qubit can take up like 2 states each, so basically that will actually lead to 2 to the power n number of different states. So it is 2 to the power of n, right? So this is also wrong. That is why, because in the option it is given n square. So if it is 2 to the power of n, then it is actually the right option. And the number 4 is that quantum computers could help us in cryptography and data security. That is also true because nowadays quantum computers have this huge application and it can have this prospective utilization also. Okay, so only correct options are A and B. So your answer is B. Sorry, number 2. Now let us discuss in a bit about qubits in this picture, from this picture over here, that what is qubit first of all. You can see from Google or from internet resources as well that qubits are fundamental unit to actually carry information in utilizing quantum methodology in systems. Okay, so it is the fundamental unit of information transfer in case of by using the quantum ideas in a system, that is called qubit. And why it is different from classical bit? Like in classical computers, the bits that are used are classical bits, but they can only take either of the 2 binary values, like 0 state and 1 state. They can either choose any of those 2. So basically qubit is first of all fundamental unit of data storage and information transfer. Fundamental unit of data storage and information transfer in quantum computers. So in classical bit, the only problem was that it did not function in the quantum mechanical manners. So basically he thought that there is a single state which is a like a mixed state that 1 second. So basically we are talking about qubits, right? So yeah, so sorry, I mixed up in certain points. Just let me give a bit. Yeah, so I was saying that the fundamental difference between a classical bit that is used in classical computers, so this is used in classical computers, and qubit is the bit that is used for quantum computers. So it is quantum bit, or in short qubit. So this qubit is the basic unit of information transfer in quantum computers. Now in classical bit, the thing is that you have 2 states, either 0 or 1, and Your classical bit can represent any of either one of the two states. It cannot represent both of them together. It can represent either one of the two states. Or in other words, it can either be in 0 or in one state, but not in both simultaneously. Right. But qubit utilizes the idea of quantum superposition principle to define the state as a linear combination of the two states 0 and 1. So we can use this 0 and 1 state as a z-axis basis state. So these are z basis states, which actually help us to get the total states actually structure. We can just take any combination out of these two basis states and form our actual state. So two z basis states are 0 and 1. 0 is defined as, let's say, 1 0, and then your one state will be defined as 0 1, right? So these are z basis states, and your classical bits can either represent the 0 state or 1 state, cannot be both. But because in quantum mechanics there is a principle called superposition principle, which says that a state can be defined as a linear combination of two different basis states, and there will be a certain amplitude or magnitude for each of these states, and if you take the whole mod square of that amplitude, you will get the probability for the system to be or to reside in that particular state. So basically you can then define a state phi as alpha times 0 plus beta times 1. So this is a linear combination of superposition principle of states that I was talking about. Here your basis states are 0 and 1, out of with which the total state has been formed, and this alpha and beta are complex numbers, which are complex magnitudes or amplitudes for the states 0 and 1, and your alpha whole mod square is the probability for the state being in 0. Okay, probability for the state for being in 0, and beta whole mod square is the probability of the state for being in the state 1. Right. So, and your total probability is your alpha whole mod square plus beta whole mod square, which is equal to 1. So basically, this actually gives you the advantage that you are not restricted in any of the single state, but it can actually represent both of the states in a linear combination form, and that is what makes the qubit much more advantageous than classical bit. And other than that, there is also the ideas of quantum interference, which actually helps to increase or decrease the total probability depending on whether the interference is constructive or destructive, right? But also there is the idea of quantum entanglement, which helps two qubits which are quantum mechanically entangled to each other. No matter how far away they are from each other, they can be infinitely far away from each other, but because they are entangled, and their quantum entanglement will still actually remain. And in that case, if you just measure the information about one of the qubits, then without measuring the other, you will be able to get the information about the other qubit in the entangled state. And these points actually makes qubits much more advantageous than classical bits. So this is a representative picture I took from a Google page. So here there is a nice demonstration that how classical bits and quantum bits can be differentiated. So in classical bits, you can see that you have a bit 1 and bit 2, both are in two different states. Bit 1 is in this white colored circle, which means that it is in empty state or zero state. So this is basically the zero state. And bit 2 is in the black field box, black field circle. So that means it is a field state or one state. So this state. But in quantum bits or qubits, that there is no specific 0 or specific 1, but rather you can see there is a circle which has both black and white present. So there is a certain probability of it being black, which is this portion, right? And it has a probability of 2/3. So this is the 2/3 portion of the whole circle. That is why it is, the probability is the amplitude is 2/3. But so and the other state, that is a zero state, which is this white part, is 1/3 probability of the system being in. So basically this qubit is a superposition or linear combination of both the states 0 and 1. So this black state here is the 1 state, and this white state here is the 0 state. And because your alpha 0 plus beta 1 is your final state, and alpha whole mod square plus beta whole mod square equal to 1. So each of the probability is 1/3 and 2/3. So that total sum becomes 1, right? And similarly, in this example, you can see that there are two separate beakers. One has 20 red balls and the other has 20 blue balls. Because red and blue are separate, so they can be identified as two separate states. One is the 0 state and the other is the 1 state. But if the beaker is such that there are both red and blue balls are present, then depending on how many balls are present in what color, so let's say 8 out of 20 balls are in the colored red, that means 8 out of 20 balls are in 0 state, but 12 out of 20 balls, that means the remaining balls are in 1 state. So the total state of this beaker can be identified as this some probability of being in 0 state and some probability of being in 1 state. So this is the qubits idea. And also you can see from here that classical bit means any of these two, like it can be either a head of the coin or like tail of a coin. So if you identify your head of the coin as 0 state, that is this state, and if you identify the tail of the coin as 1 state, that is this state, then classical bit means either head or tail, not both of them together. But quantum bit means both of them are relying together. There is a 50% chance of landing on 0 and 50% chance of landing on 1. So this is what actually makes the idea of qubit much more simpler, that because of these advantages of quantum mechanical advantages of superposition, linear combination, information transfer in entanglement way. So all these things make quantum bits quite like fancy and quite important to use. So basically it helps you to do calculations, very complex calculations, to calculate in a few minutes, which even the fastest classical computers available nowadays cannot finish till billion of years. So that is what even in a single sentence you can know how much powerful these qubits can be. Although there are some downfalls, like qubits are so sensitive to the external environment that to protect it from the other effects like noise from the environment or some other environment effects, so you have to protect the qubit in a very specific form to protect it from any kind of noise, so that it can perform properly. In that case, actually, there is another thing called topological qubits, which actually makes the whole qubit system very robust, and actually that is basically more convincing to use nowadays than the normal qubits. But anyway, to protect the qubits from noise and from thermal fluctuations, etc. So for the qubits or quantum computers in which qubits are used are generally placed or located at a very low temperature, which is close to absolute zero temperature in most of the cases. So these are some of the downfalls that to maintain and to actually properly maintain the qubits ideas will be important. Okay, so that is what actually our question was not about that. So our question was that it can store much more memory than classical bits, obviously, because it can be a linear combination of, it can represent a linear combination of two states instead of one. and because of that it can carry much more, it can store much more memory than bits, it can carry much more information than the bits. And because there are, if there are two states, two binary states available, 0 and 1 for each of these case in qubits, so for n number of qubits there will be 2 to the power of n different states, and obviously it can help us in cryptography and data security. So your option will be option number 2, which says A and D are true. Right. So then question number 4 is that choose the true statement regarding BCS wave function. So you know that BCS theory is a microscopic theory of superconductivity, which actually very nicely can explain the at least the type 1 superconductivity very nicely, and there is no other say, equivalent theory that can properly cover so much areas or domains of superconductivity and its ideas. Okay. So so let us find out that what is a true statement. So first one is that BCS wave function is an eigenstate of number operator. This is obviously wrong. Sorry, this is wrong. The number of pairs can be fixed by integrating over the phase. So this can be true because if the pairs are actually of different phases, that they can be actually fixed together if we integrate over the phase on them. So this will be like correct. Then the BCS waveform is this, where this is a summation sign over here. So basically this will not be a summation, rather the entire wave function will have a multiplication sign over k. So your true option is not also 3. So the only remaining option is sorry, the last option was the BCS wave function is not an eigenfunction of the phase. This is also incorrect because it is an eigenfunction of the phase. So that leaves us with this thing, that the only correct option is that the number of pairs can be fixed by integrating over the phase. Now why this is so? Because first of all, BCS theory has this trial wave function that works very well, is that phi BCS equal to pi k. That means we are taking the representation in momentum space. So pi k into uk plus. So generally there is, sorry, I think there is a confusion between u and v notation. So let me get that right first. Okay, so this is the multiplication over k space sign, and that is in the bracket you have to write uk 0 plus vk right. So this will be like um, what 0. So this is the trial wave function that is used in BCS. So this is a trial BCS wave function, where uk is the amplitude for 0 state still being occupied, and vk equal to amplitude for one state being occupied. So in case from amplitude you want to write down the probability, then it is uk whole mod square, and this the second one is vk whole mod square. So this is the probability of the state k up and minus k down. This state to be actually occupied, this probability is uk whole mod square. Probability of state occupied, the whole mod square is probability sorry, I just mix them up. So basically probability of k and minus k state being unoccupied or empty is uk whole mod square, and vk whole mod square is probability of this state being occupied. Similarly in this case, because uk is the coefficient corresponding to 0 state, that means it is the empty state. So basically uk will represent the probability of the state k minus k to be empty. Okay, and because vk is the amplitude coefficient part, so it is coefficient part for this second one. So basically if you take this thing, so this is the annihilation operator of this k minus k state. So this is the, not annihilation, this is the creation operator. So this is basically based on second quantization method and written in k space, so that the BCS trial wave function is written. So this is the creation wave function, creation operator, that is for the k up and minus k down state, right? And this is acting on the 0 state, which is an empty state. So obviously it will give rise to a state which is k up and minus k down being occupied, or minus k downs, k up and minus k down state being present. So that is why you can actually rename this state. When you operate the creation operator on 0 state, you will get a state which is 1. Okay, so this is the next state. So that is why you can also write this trial wave function as psi, so this product term of k into uk 0 as vk 1. Okay, and because uk and vk are both probability, so uk is the probability of being unoccupied and vk is the probability of being occupied for the state k up minus k down, and this whole probability summation will be equal to 1 as usual. And this thing works like this, that you have your probability axis in the y-axis and energy in the x-axis. Then this is the Fermi level EF. This is EF minus delta. This is EF plus delta. So then this is the case, that this is your pk whole mod square, which is 1 up to this point, and then again gradually decreasing as we are approaching the like EF, near the EF, and this is happening at t equal to 0 Kelvin. So this is the assumption that BCS theory has to make to actually work things in that way. So basically your pk whole mod square, that is the probability of the state being occupied, is obviously 1 when it is much lower than EF or Fermi level, because then the states will be occupied, just like it happens for normal metals as well. But when this uk whole mod square is the state k minus k being empty, so the probability of that will be 0 up to this point, and then slowly picks up, and then finally much beyond EF or much beyond the Fermi level, this probability uk whole mod square again becomes 1. Okay, right. So yes, this is the main idea. And as I said in this question, that there was another thing mentioned, that the BCS wave function is an eigenstate of the number operator, which is not true, because number operator, if it acts on a state and gives eigenvalue as a number or count, then only it will be called the eigenstate of the number operator. But basically it is not eigenstate of the number operator, but it is eigenstate of the phase. How phase? Because in the superconductor, all the electrons are correlated with each other, or they have a coherent phase throughout the system. So all the electrons in the system, they form Cooper pairs and they form a condensate, and the condensate in a total is represented by this condensate is actually represented by a single wave function, and that has a single phase throughout the system. So that is why this is important, that BCS wave function is not an eigenstate of number operator, but it is an eigenstate of the phase, because phase is the only thing that remains unchanged. And so basically, because superconductor is known to be having a known to have a coherent phase throughout the system, that is what is happening over here, that throughout the system all the electrons, they do not have any random relative phase, just like the other uh, normal metallic state cases. But in like superconductor, or using BCS theory, it is basically not an eigenstate of the number operator, but an eigenstate of the phase, because uh, the phase is the only thing that is coherent in the superconducting regime throughout the system. Okay. So this is also answered option number 2, right? Then in question number 5, it is asked that what is the maximum current that a wire of radius r can carry with zero resistance. So this is also very easy. You know that if your wire is of radius r, then your magnetic flux density is written as mu naught I by 2 pi r, where I is the current flowing through the system and r is the radius of the wire. So if your B equal to mu naught h, then your h will be easily I by 2 pi r. So your IC will be 2 pi r h. So then in the options it was given that IC was independent of HC, which is obviously wrong. It is directly proportional to HC, wrong. Inversely proportional to sorry, not, this is not wrong. So this is the right option. I mistake. So this is the right option, because I already have shown you that your IC is equal to 2 pi r HC. That means your IC is actually proportional to HC. So this is thing, and then inversely proportional to HC. So this is also not right, because we do not have the information about it, and then none of this above is also not correct. So the only thing that is correct here is the directly proportional to HC. So we have calculated from here that your IC equal to 2 pi r HC. That means your current is actually proportional to the magnetic field, and in other terms, the critical current IC is proportional to the critical magnetic field HC. So they are both directly proportional to each other. So it is done. Then in question number 6, it is asked that the following figure shows superconducting behavior under varying magnetic field and temperature. The graph shows magnetic flux B as a function of absolute temperature T. Then match the correct figure from the options. So it is very easy, that you have already known about this type 1 and type 2 behavior of superconductivity. In type 1, there is only one single in type 1 there is only one single critical magnetic field that is present, but in type 2 there are two critical fields that are present, BC1 and BC2, and we have to wait for correct figure in the option. So basically we have to actually ensure that we choose the correct option for the correct regime, right? So there are three regimes given, A, B and C. Your A regime is when your field is below the first critical field value BC1, then B regime is between BC1 and BC2, and C regime is beyond BC2. So you know that from the superconductor is a perfect diamagnet if it is in a pure Meissner state. So this A state is basically when the field is actually lower than BC1. So it is in Meissner's, it is in the actually the basically the Meissner state, where it repels any kind of magnetic flux from inside of it. So that is what happens, is that in A state the picture will be like this. The field lines will not penetrate the superconductor, but it will pass across the superconductor. So this is in the Meissner phase. Then in region number B, it is between BC1 and BC2. So here there comes a phase called mixed phase. or where the vortices appear in the superconductor. So in the mixed phase, it is not completely normal and not even completely superconductor. So the field lines will now be able to penetrate the sample, but through some localized regions, only through some localized regions that has turned into normal, and they are called the normal regions. And when the field lines passes through those normal regions, so that makes it a makes it a vortex in the superconductor. So this is basically the mixed phase, where the picture will be like this, that the field lines are penetrating inside the superconductor, but it is not thorough or uniform, but through some random places that is given from the film. So in other terms, superconducting material, not film, superconducting material. So basically, this is your Meissner phase, this A, this is your mixed phase, and in this phase that is beyond this BC2, this has become normal. So this is the C regime. In the normal, then all the field lines will be very easily penetrating the material. Then it will be option number 2. So your A will have a picture like this, B will have a picture like this, and C will have a picture like this. So what I said is that for type 2 superconductors, there are two critical field values present. The first critical field value is up to which it is purely in the superconducting phase or pure Meissner state, where it completely repels out any magnetic field that is present there. So that is why the diagram looks like this. The field lines are all repelled out by the superconductor sample. But between BC1 and BC2, because it has crossed the initial or the first critical field, so it has not remained as a pure superconducting state, but that's why it is called a mixed state, because inside a superconducting background there are normal localized regimes that are present through which field lines can still penetrate. So they are called vortices, and this diagram looks like this one, where the localized red spots, you can see from here that this spot and this spot and this spot, from here from where the vortices is present. So this will cause the flux line penetration. And then in the regime C, which is again beyond BC2, which is the second critical field value, even beyond that, so in that regime, that will turn into a normal state, because it has no mixed phase anymore. It will be a completely normal state, and the picture will be looking like this. All the field lines are penetrating uniformly through the sample as it was doing in the outside regime. So the option will be A equal to 1, B equal to 3, and C equal to 2. So this option number 2 is right. Then question number 7 is that the quantum of magnetic flux in a superconductor in CGS unit is given by. This is very easy, because we know that the flux quantum has a formula in SI as h by 2e, but because it is asked in CGS unit, so you have to include the light's velocity c in that. Otherwise, it is hc by 2. Okay, where h is the Planck's constant, c is the velocity or speed of light, and 2e is from the Cooper pair charge. So generally it is single charge for a single electron, but because it is a Cooper pair in a superconductor, so this is a Cooper pair charge for the 2 electron. And the magnetic flux has a quantum of hc by 2. So we have to remember that it is hc by 2. Now question number 8 is that for a superconductor, the critical magnetic field, we know the obvious answer, that the critical magnetic field increases with decrease of temperature. You can also answer this from the formula, if you remember, that BCT equal to BC0 1 minus T by Tc whole square. So at T equal to 0 Kelvin, so this term will vanish. So then BCT equal to BC0. But as T increases, or as the temperature was increasing, so then 1 minus T by Tc whole square becomes not sufficient. Then only there is this whole other BCT term present. So other than that, if you just take that T equal to 0, BC equal to BC0, which is the maximum value, but if your which is a minimum value actually. No, sorry. So let us draw the diagram. So this is the diagram that this is your BCD and this is your temperature. This is your TC. This is your T equal to 0 Kelvin. So this is the BC0. And then as temperature increases, this second term increases. So 1 minus this T term will be decreasing, and that is why BC0 will be decreasing. So you see that at T equal to 0, BC0 is the highest or maximum. But at as you increase the temperature from here or here, you can see that according to the graph only the BC value is decreasing. So in other words, if you decrease the temperature, the critical field value actually increases, because if you go from TC to up to low temperature 0 Kelvin, you will see that you will go this way, then the critical field value will increase obviously, because as you decrease the temperature, that means you are going much more deeper inside the superconducting regime. Even if you are below TC, then that means you are in the superconducting regime. But with decrease of temperature, you can go much further and deeper into the superconducting regime, and this will actually cause the critical magnetic field of the superconductor to increase. Because now, even if you apply a very strong magnetic field, it will not instantaneously turn the superconducting material into a normal material. So that is the whole thing, and the other options are not correct. Then question number 9 says that from the following statements, choose the correct option related to qubits. We know that the orthogonal z-axis basis states of the qubits are defined as 0 and 1. That is true. Then it is that two orthogonal x basis states are given by this plus equal to 0 plus 1k divided by root over 2, then 0 minus 1k divided by root over of 2. So these are orthogonal x basis states. So this is given by this a linear combination of both the states 0 and 1, as sir asked in the this thing. So basically, two orthogonal x basis states are given by 0 plus I1 divided by root over 2. This is not correct, because the option number 2 B is correct. Then D is that if there are n qubits in a quantum computer, then it will have n square different states. This is also not correct, because I already told you in an earlier question that for n qubits there will be 2 to the power n number of states. This is also wrong. And z basis states are 0 and 1, because they are defined as either 1 0 and 0 1. And x basis states are defined as 1 by root over 2 is the denormalization factor, normalization factor, then 0 plus 1, and other thing is 0 minus 1. And this is with I, this is not the x basis state, but you can just for your knowledge sake, you can know that the y basis states are 0 plus I1 divided by root over of 2 and 0 minus I1 divided by root over of 2. These are y basis states. Okay. So this is done. Then question number 10 is that a Josephson junction operating an AC frequency of some 482.9 megahertz has a voltage of n microvolt across its terminals. Then what is the value of n? So this is a Josephson junction problem, and also this is AC Josephson junction. We have already discussed in detail about Josephson junction and Josephson effect, and in the last tutorial you can follow that. And there we have learned that if there is a bias voltage, non-zero bias voltage applied, V not equal to 0, then it becomes an AC Josephson effect, because in that case the change in phase with time d delta dt equal to 2e V by h cut, where V is the bias voltage, and hence if you integrate it, your phase will have a time dependence as well, that is it will be dynamic, so it will be 2e V by h cut into t plus some constant time independent phase delta. Okay. And depending on this, the current will be decided across the junction as I equal to IC sin delta. But from here, if you just look at it, because delta is phase, that means phase will be dimensionless in a sense. So if there is a t term here, so obviously there has to be something that cancels this dimension of t. So if this is time, then this other part will have to be frequency, so that the overall factor becomes a phase. Okay. So that is why we call our frequency nu as 2ev by h cut for a Josephson junction, and also this is in AC. So this is AC Josephson junction and the frequency is 2ev by h cut. Now it is asked in the question that what is the value of V in n microvolt. Okay, so what is n? So you have to calculate V first. So V equal to nu times h cut by 2e. So nu equal to 482.9 megahertz. So this is 0.9 megahertz is 10 to the power 6 hertz into h cut is 6.634 into 10 to the power of minus 34 divided by 2 pi is h by 2 pi into 2 into 1.6 into 10 to the power of minus 9. So just we calculate this, and this becomes 482.9 into 10 to the power of 6 into 6.63 into 10 to the power of minus 34 divided by 2 into pi into so there is a 2 present or 1. Yeah, so this is a 2 pi and then 2e. So 2 into 1.6 into 10 to the power of minus 9. So this is around 1.59 into 10 to the power of minus 7 volt. Or this is 0.159. So this is 1.59 10 to the power of minus 6 10 to the power of minus 1 volt. This is equal to 0.159 10 to the power of minus 6 volt. So this will be roughly equal to this is roughly equal to 0.159 microvolt. So let us just check whether the calculation I have done is right or not. So the frequency was, formula is correct. The frequency was 42.9 megahertz and H is taken to be 6.626 into the power minus 34, 482.9 megahertz. So here is nu equal to 2ev by h cut. So V equal to nu h cut by 2e, which is 482.9 into the power 6 hertz into 6.626. 6.626 the Planck's constant value into 10 to the power minus 34 divided by 2 pi, because h cut equal to h by 2 pi into 2e, 2 into 10, 1.6 into 10 to the power minus 19. So if you just divide it, you will get 482.9 into 10 to the power of 6 into 6.626 into 10 to the power of minus 34 divided by 2 into pi into 2 into 1.6 into 10 to the power of minus 9. Okay, so this is 0.159 microvolt. So this is even less than 1. So n value, the nearest integer if you want to take, this is just 1. Otherwise, this other no nearest integer is present there. So this is also taken care of. So basically in this problem set, we have discussed problems about how to calculate the critical field value with temperature, varying with temperature. So the basic formula we have to use is the BC, P equal to BC0 1 minus T by Tc whole square, and then depending on that we have to guess what is the radius of the wire for a current carrying wire producing that magnetic field. So then we simply have to use the electrodynamics formula of magnetic field from a wire, which is equal to mu naught I by 2 pi r equal to magnetic flux density. And then there are some questions about quantum bits or qubits and quantum computation, which is again the fundamental unit of information processing and transfer in quantum computation is qubits, and it can way faster and smoother than actually classical bits that we have also discussed. And finally there is also discussion about BCS wave function. That BCS theory is a microscopic theory of superconductivity where it is assumed that it is a linear combination of both the states, that is it has both momentum states as empty and momentum states as fallen. So basically this is the main formula of this BCS trial wave function in the momentum space and under second quantization, where the creation of operator C Ragged has been used, where you can see that 0 is a vacuum state or empty state you can say, and UK is with the direct coefficient of U, because UK or U suffix K is actually because it is a coefficient of 0 K, that means there is one thing is in the 0 state and the other linear combination is with respect to the BK creation operator 0 state. So if you just operate the creation operator on the 0 state, will make the state 1. So that is what is happening, that this product of K, UK plus VK, the first term will be 0 and the second term K will be 1. Okay, so and the probability of the state being in any of the states is let's say K up and minus K down state in momentum space. The probability of the state being occupied is Vk whole mod square, and the probability of the state being unoccupied is actually given by UK whole mod square. So you can also clearly see from this picture that about EF or the Fermi level, the states are actually which are occupied first are actually becoming empty, so it is going from 1 to 0, and on the other hand the critical field value is actually given by this formula. And obviously BCS theory actually gives you the idea that superconducting wave function is a single wave function for all the Cooper pairs in the superconductor, because they are coherent and strongly like they are coherent and behave in a coherent manner. So that is why all the Cooper pairs in the superconductor has a single phase phi, and that is why they are called the eigenstate of the phase as well, because only the phase is actually a single phase for all the combined carriers of Cooper pairs in the superconductor. Okay, so they are assigned with a single phase phi. So that is why BCS wave function is an eigenstate of the phase but not the number operator. So that is why option number 2 is correct. And then it was discussed again about the relation between the cylindrical wire radius and the current flow and the magnetic field density that is produces. So this is discussed in this problem. Then question number 6 was about which statement, which regime was which graph, and that tells us that there are 3 different regimes between for field that is below BC1 is the phase of A, where it is in the pure Meissner state. That means field lines completely deviate or being repelled by the superconductor. And then between BC1 and BC2, this is neither complete superconductor not completely normal. So there are separate local regimes within which the current or the flux lines can pass through. So this is the called the mixed phase, and in that case the diagram will be like number 3. And then for the region of C, the value of this the nature of these lines will be, flux lines will be option number 2, because that is the only left out option. And also the other thing is that because it is more uniform throughout the sample uh, compared to the other thing. Okay, so we have also calculated that. And question number 7 is about the quantum flux unit, the quantum anti-flux quantum unit. So that is hc by 2e, that is already well known. And then superconductor, how this Bc value changes with temperature, is that if the temperature is very low, then the critical field will have to be very high, or it will have to increase. So, and then question number 9 was again for qubits, and their x basis states are also given, as well as y basis states. Then question number 10 is again about Josephson junction and the AC frequency and the voltage, etc. So with this, our option tutorial number 2, tutorial number 8 is finished, and this is the final tutorial of this course. So we stop here.